Welcome to NRM 435 GIS Analysis, Spring Semester 2018. This is a class at the University of Alaska Fairbanks. And in this class, we're not going to worry about data. We're going to assume that you have existing GIS data and your data are high quality and all your data are in the same correct coordinate system. So assuming you've got good GIS data, what type of questions can you answer using GIS? So in this class, we'll answer questions via the analysis of points, lines, polygons, rasters, and 3D data. The first half of the class will be working with geoprocessing tools for features or points, lines, and polygons analyses. So for example, our first lab will work with point analysis, looking at fictitious animals' home range and how those point locations differ compared to random points. So in this example, the animal locations are delineated by black points, and these red points are randomly located points within this animal's home range. And then we'll also work with tools for estimating point densities, estimating polygons from points, creating polygons of proximity, and then interpolating values among points that are quantities. The next week we'll work with tools for line analysis. So here's an example. We've got radio-colored grizzly bears, and we've got a line layer representing streams, and we want to know what's the density of bears by bear ID within 1 kilometer of a salmon stream, within 1 to 2 kilometers of a salmon stream, 2 to 5 kilometers of a salmon stream, etc. The next week we'll work with a special type of lines called measured lines. So in this example, we've got for every stream a count of sockeye salmon, king salmon, and silver salmon for every 50-meter stretch. So from 0 to 50 meters, 50 to 100 meters, 100 to 50 meters, etc. And then using tools, we can ask questions about these salmon counts along these measured lines. So for example, where is the maximum silver salmon count for a 50-meter stretch? That would be in this stretch. Where's the maximum sockeye salmon count in 50-meter stretch? That would be that 50-meter stretch. And where's the maximum Chinook or king salmon count per 50-meter stretch? So that would be that 50-meter stretch. The next week, we'll work with specialized tools for network analysis. So for example, we want to go from point A to point B. Driving the speed limit give us the quickest way to get from point A to point B. Or we're walking, we want to minimize distance, so give us the least distance route from going from point A to point B. Or we have fire stations, and we've got 10 fire stations in the city. Find the 2 closest fire stations to this incident, which is a fire, and then give us the directions for these 2 closest fire stations. So we'll have all sorts of questions dealing with network analysis. Then the next week, we'll work with tools for polygon analysis. So here's an example. Show us all the saw timber polygons by species type that are at least 100 meters away from the wetland and at least within 1 kilometer of an existing road. And then the next week we'll deal with tools for answering questions about overlap and adjacency. So for example, here are all the burns in Alaska in the decade of the 1990s, and here are all the burns in Alaska from 1960 to 1989. So find the largest repeat burn between those 2 time periods. So here's the largest repeat burn, an area that burned from 1960 to 1989 and then burned again in 1990. So that would be an overlap type question. An adjacency type question, find the border between balsam poplar and white spruce within the Tanana Flats zone and find all the borders greater than 100 meters And for those borders that are greater than 100 meters, label the length of those border lines. So for example, here's a border we can boat to along the Tanana River, and then we could sample along that border, and it's 545.5 meters long. And then the next week we'll deal with movement, so animating movement and asking questions about movement. So here's an example of two fish located as points every hour, and they're moving upstream. And then we'll have random paths. What is the percentage by vegetation type for these random paths through the landscape compared to an actual path that the animal traveled throughout the landscape? And then estimating animal home ranges from animal locations. And then we have spring break, the middle of March. And then when we come back from spring break, we're going to leave the analysis of points, lines, and polygons and start analyzing rasters or grids. So the first raster analysis week, we'll use tools to answer a similar question that we answered in the point, line, and polygon world. Find all the saw timber that's close to a road but far away from a wetland using raster analysis tools. So in this case, all these layers are rasters that are 10-meter grid cells. And then the next week we'll have a path analysis where we have rasters representing cost surfaces. So one cost surface might be lakes, and it's too costly to build a bridge across the lakes, so there are barriers. Another cost surface will be streams, and it's much more costly to build a bridge across a stream. So find from this existing road the least cost path to go from anywhere on this existing road to this target resource and minimize the cost. So this is the path that minimizes the cost. We only cross one stream, so we'd have to build a bridge across that one stream. And then the next week we'll deal with the analysis of elevation data from Lidar. So Lidar is a laser-based high-resolution elevation where we have what's the elevation to the top of the canopy, what's the elevation to the base or the ground. So if we subtract the first return minus the ground return, we would have the canopy height. So here's an example. For each polygon, give us the average height in meters. So for example, this is a spruce stand, and the average height of this spruce stand is 6 meters. And then we could have stands that are down in the alluvial bars that are willow stands, and their average height is less than 1 meter. And then the next week we'll use elevation rasters to delineate watersheds. So here's a watershed that was delineated manually by going along the ridge lines of the contours. And then this area in cyan is the watershed that was delineated using an automated watershed routine. And then the next week we'll work with 3D analysis. So here's an example where we have a gravel pit in 1 year, and then we're extracting gravel from the bottom of the pit. So here's what the gravel pit looks like in 3D the next year. And then we could calculate how many cubic meters of gravel were removed between this first year and the next year. And then the last week we'll deal with how to analyze GIS data to assess its data quality.